All right, we're going to jump back into section 8.4. The beginning of 8.4, we looked at basically characteristics of lines. We talked about slope, we talked about ways of writing lines and things like that, but we basically looked at lines. The second half of this section, we're going to look at two lines at one time. And more specifically, the name of that is actually systems of equations. So we're working with linear ones. So these are systems of linear equations. So a system of linear equations is a set of equations, usually with more than one variable in each equation. The solution to a system of equations is an ordered pair that is a solution to both of them. It belongs to each of the lines. So it is a point that lies on both lines. It's an XY ordered pair common to or satisfying both equations. And in terms of a graph, it's their intersection where they cross. We're going to focus on two ways of finding this point where they cross. There are more ways. One way we're not going to talk about is graphical. It's a great way of talking about it. It works really nicely if you're very visual. It doesn't work very nicely if they don't cross on a whole, like an actual corner of an XY ordered pair, like whole numbers. It doesn't work very well. It doesn't work very well if the numbers are sort of more real life equation stuff, like the cost of, buying the Sonic drink or whatever. I mean, it doesn't work very well for real life data. Another possibility of systems of linear equations being solved is with matrices. That's high school stuff, so we're not talking about that option either, but those are a couple other ways that could be used for solving. So the first one that we're going to use is called the substitution method. The substitution method is a series of steps which basically allows you to take and substitute from one equation into the other. So what we do is we solve one equation for one variable. It's our choice, which means that we have flexibility. The second step is to substitute this value into the other equation. Step 3 is to solve the resulting equation, much like we did earlier in 8.4, solving. Step 4 is to back substitute the answer into the first equation. So if you found x, you put it back in to find y. If you found y, you put it back in to find x. And then step 5 is to check the solution, at least mentally, by plugging both values into the equations. So I've been talking about checking solutions in my college algebra class during this week. Checking solutions is sometimes required because sometimes solutions end up not working. Like you didn't do anything wrong and they're just really not a solution. And sometimes sometimes when we're checking solutions, we're doing so just to make sure we didn't make a mistake. That's the category that you're looking at here. So if you don't get it to work out, you have in fact made a mistake. It's not just that it didn't work and so now we're done. We have to go back and find our mistake. And then the last step is to either write it as an ordered pair, if you're working with strictly algebraic equations. But if you're working with context, you might instead write it with units, right? It's 15 adults and 13 children, not 15, 13. That doesn't make sense in the context if we have units to associate. So we're going to focus on looking at this within context. And the first one that we're going to do is a movie theater example. Fun fact, I think we're taking our kids to the movies tonight. We like the movies. We've been so sad at not being at the movies over the past almost a year now. All right, at a movie theater, a child's ticket costs $5. An adult ticket costs $8. On Memorial Day, the theater counted 562 audience members. They had a total of $3,785 in ticket sales. The question is, how many child tickets were sold and how many adult tickets were sold? Okay, do you have a picture in your mind of what they've done? Okay, good. So we're going to start by deciding what we are what we don't know or want to find, and assigning variables to that. So this one tells us at the end that we want to find the child tickets and the adult tickets. So we're just going to let those be X and Y. If you want to use letters that look more like the words, like C for child and A for adult, you can do that. Sometimes people like that to keep their mind straight on that. Either way, it doesn't really matter. So my X is going to be my number of child tickets sold. And my Y is going to be the number of adult tickets sold. Okay, so far so good? Now there are two pieces of information that they actually give us inside of the system, or the words about the system above. They gave us information about the sales in terms of how many people, and they give us the information of the sales in terms of their profit, or maybe not profit, but at least ticket sales value, right? The money that was coming in. So those are the two equations that we're going to set up. We're going to set up one equation talking about the number of tickets, and equation 2, that was equation 1. And equation 2 talking about the money that's being discussed. So let's talk about numbers of tickets. How can I use the variables that we've created, X and Y, and the information they give me about the ticket numbers that were sold to create an equation? What would it be? Right. So X plus Y equals 562. Does that make sense? Okay, add the child tickets, add the adult tickets. We have a total of 562. How can I use the other information? It's the harder of the two questions, right? Equations. How can I use the other information to create an equation about the money that came in? Okay, Emma, that was you, right? That's perfect. How did you get it?
The amount the tickets cost. So I matched the dollars sign with the dollar sign.
Okay, so it's $5 for a child ticket and X tickets are sold, right? So if I multiply the number of tickets times the cost of the tickets, that's what I would get total. It's the same thing that I ask you to do when you're looking at your test redos and asking you to take the last number after the R times 3. There's 5 problems, 3 points each, that's 15 points, right? The 8Y does the same thing, $8 for an adult ticket, Y tickets sold, and then the total amount of money that is collected is $3,785. Okay, so these are my equations. We have the problem set up now. We're actually needing to do the substitution method over here to solve it. That's where we are. So the first statement in this method actually says we need to take one equation and solve for one variable. It is our choice. We get to pick the equation and we get to pick the variable. And there are choices that are nice and there are choices that are not nice. So what would be a nice choice of an equation and a variable to solve for? We'll call this one equation 1 and this one equation 2. Awesome. Okay. So I agree with you, Elizabeth. I think it would be very nice to take equation 1 for sure, right? Why? Well, because it's a lot easier to solve for X or Y in equation 1 than in equation 2. Because they don't have a coefficient that's not 1, right? So, and then we can pick, and it really doesn't matter what we pick. Elizabeth picked X, so that's what we're going to do. We're going to solve this one for X. So I have X plus Y equals 562. I would subtract my Y. So X is 562 minus Y. So this is step number 1. Let me go back and relabel these so that I'm not confusing my 1s and 2s. We'll call this equation A and this equation B. Okay, step number 1, okay? Okay, step number 2 is sort of the crux of everything that's going on. It's the substitution step. So it says that we take the equation we didn't just take, which for us was equation B. So we had 5x plus 8y equals 3,785. And we're going to replace x with what x is equal to. So x is 562 minus y, right? So this x right here gets replaced with 562 minus y. So we're still at 5. I have 562 minus y. Still have plus 8y, and it still equals 3,785. All right, so far so good? That's step 2. Step 3 is to solve that. So we're going to distribute, we're going to collect like terms, and in the very end it's going to end up saying y equals something. So we have this multiplication. So 5 times 562, excuse me, is 2810 minus 5y plus 8y equals 3,785. Okay. I'm going to do 2 steps at once just because I'm running out of space a little bit here. I'm going to move this over too. I'm going to move my 2810 to the other side. And I'm going to combine the 5y and the 8y, negative 5y and 8y. So negative 5y and 8y would be 3y. 3785 minus 2810 is actually 975. And what would be our next step then to solve that? Yep, divide by 3. So we'll divide by 3. And what is y? $3.25 is right. So that's the end of step 3. All right, I was looking to see if I had left me space on another slide, and I have not. So I'm just going to shrink some things because I don't really want them to disappear in case we need to reference them later. I'll disappear these though. All right, I think that's still pretty much all there then. Okay, so that was step 3. Step 4 is back substitute. So step 4 says I'm going to try and figure out whatever the other variable was. So one variable is x, the other variable is y. I found y already. That was in step 3. So I use whichever equation that I have that's easiest to solve, and the one that's easiest to do is the one that's highlighted in yellow because it already says x equals something. So I can write down x equals 562 minus this value y, which is 325. And what will x equal? 237 is right. Now, I'm not going to write down step 5, but it wouldn't be a bad idea for us to actually use a calculator to verify step 5. Step 5 is checking the solution. So my 2 answers to the question have to do with what y is and what x is. So x and y were ticket sales, right? And one of our equations says that the total number of tickets sold is 562. So we can confirm that if you add these 2 together, you get 562. And that one works out pretty quick. The other one is that it really works for our dollar amount. So if you were to take your calculator and take 5 times 237 plus the 8 times the 325, we want to check to make sure that it will equal 3,785. Does it work? Good. So sort of we did step 5. I'm just going to write that we've checked it, not because I care if you write that down, but I just want you, if you look back at your notes, not to think we skipped a step. We checked it. At least mentally, we've checked it. Step 6 is to write out the solution with context, because we're dealing with problems with context. So, solution. Well, the solution is that we're going to write down each of my values with what they are. So what is the 325? Adult tickets. And that makes the 237 the children. And this would be the solution to our system of equations. Is that okay? I know that this is not the first time you have seen substitution, but I want to make sure everybody's good with it and comfortable with it before we move on. Okay. The other method we're going to talk about is the elimination method, although I should let you know that some books call this the addition method. Our current college algebra book calls it the addition method. So the elimination method, or addition method. Step 1, if necessary, multiply both sides of the equation by a suitable number so that one of the variables will be eliminated when we add the equation. The second step then is to add the equations, which will eliminate something, and solve what you have left. Step 3 is to back substitute to find the other variable. And then steps 4 and 5 are much like they were before. Check the solution at least mentally, make sure it works, and then write the solution as an ordered pair or with units. All right, so let's go ahead and do an example of one. At a bake sale, Cassandra sells 4 muffins and 6 cookies for a total of $18. Okay, so we know how many muffins, we know how many cookies, we know how much money she makes. Michelle sells 3 muffins and 11 cookies for a total of $20. How much does a muffin cost and how much does a cookie cost? So we're going to start very much like the last problem with giving names, variable names, to the quantities we do not know. So what is it that we do not know and want to find in this problem? The costs, right? So again, we can pick the variables we like. I do tend to pick x's and y's a lot, but if you don't like that, choose something different. And I'm just going to go in order. It mentions muffins first, so we're going to start with muffins. So x is the cost of a muffin. Now notice how this is different than the last problem. The last problem, I knew the costs of the tickets. I didn't know how many of each were sold. This time I know how many of each were sold. I don't know what the prices are. So this is the cost of a muffin, and then y will be the cost of a cookie. Yes, Asia?
Does it matter that we have 2 different people selling them for different prices?
No, they aren't selling them for different prices. They're selling them for the same price. They're just selling a different number of them, which yields them a different amount that they collect.
Oh.
Yeah. So kind of imagine, they're working in the same store, making sales with different cash registers or something like that. So they're not competing. We could do a problem where they were competing, but that's not what's happening here. This is just a total that they are comparing at the end. That's a great question. Okay. Now, the 2 people who are selling them, though, Cassandra and Michelle, are the ones where we're getting, are the places where we're getting our information for creating the equations. So let's start with the first one, which is Cassandra. Cassandra sells 4 muffins and 6 cookies for a total of $18. So if she sells 4 muffins, and muffins cost X dollars, how much money? I don't look looking for a number value, but how much money are we looking for that being represented in terms of the x? 4x. The 4 muffins times the cost of the muffin gives me the total amount of money I make when I sell my muffins. Okay? So Cassandra's first, and she has 4x plus, and then we have the muffins or the cookies. And she has 6 cookies. So what will I do with that one? 6y. And what I've actually found out is how much money do we make for muffins plus how much money do we make for cookies, and how much money does she make total? 18. So this is equal to 18. All right, the other person selling is Michelle. By the way, these are the names of Dr. Marsh's sister-in-laws. She created this problem, and I just stole it from her. We steal stuff from each other all the time. It's okay. It's all good rapport. It's good stuff. Michelle, what will her equation look like? Mm-hmm. Okay, did I get it all written in there right? I think I did. Okay, so first of all, I kind of like to make a mental note with you, or a verbal note with you, I should say, that this problem would not be very fun to do with the last method. Because at this point, we'd have to take one of the equations and solve for one of the variables, and there's coefficients on every variable. So it really does not lend itself very well to solving with substitution. It's not too bad to solve it with elimination, though. What I need is I need one of the coefficients in the front of the numbers to match. In other words, I need the values in front of the x's to match, but with opposite signs, or I need the values in front of the y's to match, but with opposite signs. And it really is very irrelevant which one you pick. Sometimes there's an easier choice than others. On this one, there's really not a better option than others. So if I were looking at this one, what I would notice is that we'll just do x just because it comes first, that the x's don't have anything in common, right? 4 and 3 don't have any factors in common. I can't sort of multiply one by something and get the other one that's not fractional. So the easiest thing to do is to simply multiply them by one another. It's kind of like getting common denominators on fractions. I'm going to multiply this one by 3 and this one by 4. And one of them needs to be multiplied by a negative. I'm just going to do the one on top. If you want to do the one on bottom, just so you can see it works out the same, go for it. You do need to remember that when you multiply the equation by, say, -3, you multiply every piece by -3. So I have -3 times 4x, that's -12x. I have -3 times 6y, that's -18y. And I have -3 times 18, and I don't think you have that written down. What's that one? 54. And now we're going to do the second equation and multiply 3 by 4. 3x times 4 is 12x. 11y times 4 is 44y. Okay, this isn't working. Oh, that's what's wrong. I didn't get that to say minus. It actually says, or say plus, it says minus. There we go. No, it was supposed to say minus because I'm subtracting. I multiplied through by negative. My bad. Okay, I'm on to the 20 times 4. That's 80. All right, so I think I got them all in there now. So why did we want to do it, and why specifically that way? Well, we wanted to do it that way so that you can see that you have the -12x and the +12x, that if we add them together give me 0. So it's sort of like I'm doing an old-fashioned addition problem where I just add down the columns, right, where I don't have to worry about any borrowing or carrying or subtracting, or none of that stuff is going on. It's just adding straight down. The -12x and the +12x add to 0. I have -18y and +44y. What does that give me? 26y. And then I have -54 and +80, which gives me 26. And if I were to divide by 26, I'll get a 1. So y is 1. The not so nice thing about elimination in general is that I don't necessarily have a lovely place to take the 1 and plug it back into that's already solved, right? I had that over here. The highlighted yellow one was just really nice. It was already solved for x, and it just was a very natural choice for me to plug it in there. I don't have that here. I just have to pick one. So I'll just pick the top one that we started with right up here. And I'm going to plug the value of y = 1 in there. So I have 4x plus 6 times, was it 6 times 1? Yes. And it equals 18. And we're going to simplify. So I have 4x plus 6 equals 18. That's going to give me 4x equals 12. And if I divide by 4, what is x? Yeah, x is 3. Okay, so we can check to make sure that works by taking y is 1, x is 3, plugging them back into both the equations for Cassandra and the equations for Michelle, and making sure that they work. So I'll leave that as, if you will, an exercise to the reader. That you know how to do that since we talked about that before. Let's make sure that we do write down our answer, though, in terms of the units being asked. What does the 1 mean? Yeah, so the cookie costs $1. And then that means the other one, which is the muffin, costs $3. Better be a giant muffin. Okay, any questions on that? Our last little bit right here works through very quickly, so let's take a look together. A system of equations could have one solution. That's what happened on the last two systems. What happens graphically, if that's the case, is that there is one place where they intersect, right? In terms of this, we're talking about two lines crossing at one location. The second possibility is a system could have no solutions. Graphically, there's no intersection. This happens when the lines are parallel. And then the last possibility is that a system could have infinitely many solutions. And what that really means is that the two equations are the same line. They're just different versions of the same line or the same graph. So we're going to do two really quick problems where we don't have any context now and identify either that it has one solution, no solutions, or infinitely many solutions. So I have x minus y equals 1 and 2x minus y equals 5. We're going to use elimination on this one. It doesn't really matter which one we use. You'll notice that the y's already almost match. They're just the wrong signs, the same signs, right? Like they don't have opposite signs. So we can just take one equation. I'll just take the first one and multiply by -1. So now I have negative x plus y equals -1. I have 2x minus y equals 5. And of course, these add to 0. At the front, I have negative x and 2x, which gives me a positive 1x. And at the back, I have -1 and 5, which gives me 4. I can find the corresponding value for y by taking either equation. I'll just take the first one the way it was originally given to me. X minus y equals 1. So x is 4. You can probably tell me what has to go in this blank to get it 1 through here on the other side. What would I have to be subtracting? 3, right? Or you can actually go through the subtraction of the 4 and so forth. But it's a 3. Y has to be 3. So my ordered pair, we didn't write these down before because they had context, but the solution would be the point x equals 4, y equals 3. And we would write it as an ordered pair. Sort of jumped over the check step. I've already sort of checked it into the first equation. That's how I found y equal 3. We could check pretty quick mentally within the second equation. 2 times 4 is 8. 8 minus 3, it's 5. So we've got the right solution. And if we were simply told to tell them how many, there is one solution. So what would happen if there were infinitely many solutions? Well, if I tried to do this and were infinitely many solutions, I would end up either getting everything to zero out on both sides, or I would very quickly realize that the two equations, once I got something to match, were exactly identical already. Okay? So you might look at this and say, well, I know it's got one solution. How do I know that it doesn't have more? Well, that's how. It's because one solution never presents itself out like this if there's more than just one. Let's try one more. 2x minus y equals 1, and 2y minus 4x equals 3. So hopefully you notice first off that they're not lined up. Did you notice? Okay, so let's go ahead and get them lined up before we do too much else. We usually see x written first, so I'll keep that one first, which is the first equation, and I'll rewrite the second one. So it's negative 4x plus 2y equals 3. I can pretty quickly multiply the top equation by 2 so that the x's will cancel. And you can do this with substitution as well. It doesn't have to be the elimination method I'm using right now, but you could. I don't know why I wrote 3. 2 is what I meant to write. There we go. So that's 4x minus 2y equals 2. I have negative 4x plus 2y equals 3. So my goal when I made my choice to add to 0 does in fact give me 4x and negative 4x equals 0, but something unintentional sort of happened. What? The y's also cancel. So what does it mean? Well, it means that there's nothing left on the left. And if it were true that the 0 on the right, the answer would be infinitely many solutions, but it's not. What's on the right? 5. And 0 most certainly does not equal 5. So what does that mean? Well, yeah, no solution. What it really means is that we have parallel lines. They have the same slope, but they have different y-intercepts. So this would be no solution. Again, if it said 0 equals 0 at the end or 5 equals 5 at the end, then the answer would be infinitely many solutions. Any questions? All right, wonderful. So your group work is now assigned. If you will find your peoples, wherever they are in the room. I know I need to get you guys new partners, and I totally forgot about that until I just now said find your people. So go ahead and find, if your person's here, that person to work with. If not, then you're welcome to work alone if you really want to, or you're welcome to join up with another group. No more than 3 per group, and I'll get you new peoples next time just so that we can kind of shuffle it up a little bit.